Hi everyone, my name is Mikhail Rodin.
This is the Frontiers of Historical Research channel, and welcome to the Paleosurface project, where we explore the millennia that lie beneath your feet.
Now we are in the south of Iraq, and we are dealing with an archaeological site which is in the sediment environment of the Euphrat River, and it was a Isian Lhasa period settlement, maybe Babylonian. We are here to make a city map of the area and to explain the features, the houses, and maybe give some rough dating on the layout of the city. We have also nice experience from Uruk and from Ur, Farah and Isin, what we did so far. And the main question was in the beginning how to find mud brick features in the surrounding mud. So that was because it's physically the same material, but it changed as soon as people use the mud brick, bake it, and change the source of the bricks. Sometimes they add some reeds or some straw to make it easier to work, and this tiny little difference in the composition makes also a difference in the magnetic properties, and that's what we measure here. And this is that was a challenge in the year 2000, first time to make such a measurement. But since our long-lasting experience, we know that it will work here, and we will not only find kilns, but moreover we found also canal system. We now understand also how the bridges, how the roads are organized, the roads or the pathways. We cannot say roads of nowadays. You have to imagine there is rain season or even a few days of rain. You simply cannot walk on the bare ground. So what the ancient people are doing, they use old pottery and pave their little roads with this pottery, and that makes it extremely magnetic and very nicely visible for our measurements in the magnetic image. And the other way around is the canals, which consists of sedimentation of very fine sediments after years of fill up with the sedimentation, and they contain very little heavy minerals because it was not a quick, fast flow of the river. So, and all these features are nicely recognizable in our measurements. And finally, we can produce a blueprint of a city. So at least some kind of city map, and with the help of archaeologists and an understanding of construction of houses, we can provide a rough dating already, yeah? And you have a street system, then you understand how the city is organized, where are the main buildings, where are the administrative buildings, where are the palaces, the temples, and so on. So all these features which are per definition necessary to call a place a city and not a village can be found very clearly in our results. Now, right now we are doing magnetometer prospecting with a total field magnetometer. We scan the area, we do it in a gridding system. So we made 40 by 40 meter grids, and then line by line we take on the magnetic values above the ground, so 30 centimeters above the ground. And by doing this, by data processing, we have a view beneath the ground, such like a X-ray image from bones in medicine. The main thing that we do a 40 by 40 meter grid. So we walk 40 meter profile. During switch on the instrument, it measures 10 times a second, and every 5 meters we press the switch to get a marker on the ground and then to recalculate the speed of the walking speed, because we probably cannot go in the same speed all the day. So by doing this, we get a very precise points on the ground. So let's say every 10 to 12 centimeter is the spatial resolution of the measurement. And the magnetic field here, we have 46,000 nanotesla, and we measure deviation of a few nanotesla, which gives us the information about the features beneath the ground. So it's a very, very sensitive instrument. We measure about 1/50 millionth part of the Earth's magnetic field. To have an idea, Earth's magnetic field is the strength who make the compass needle towards north, and divided by 50 millionths, this is the sensitivity what we measure here. It's necessary to hold it always roughly 30 centimeters above ground, because the magnetic field is a potential field. When you move it about a little bit, then it changes up to 10 to the minus 3. So it's a very high difference if you have higher or lower distance from the ground. All these cities developed because there was a surrounding of water and water supply and a lot of possibility to grow crops and vegetables to maintain the food for the city. And as you know, when there is rain, it's hard to move in the ground. So it's very useful only to use ships and boats to transport systems. And that was a thing which was not really recognized in previous time. It was for the first time in Uruk that Margarethe van Es had the idea, let's have a look if the city is organized also by canals and not only by streets. Like it is, for example, in Ur, where we have this burnt material everywhere. But in Uruk we found huge canals, and we found that all the city is organized by little canals. And here we immediately saw also that there are canals. And if you have a city which is somehow has some administration, they should have a harbor to get goods from outside. Even the little stones here, the basalt stones and these grinding stones, they come from outside. Here is nothing. It's only mud, and they must be transported and probably by boats. Not probably, but for sure with boats. And here in our measurements we saw immediately that the entire city is organized by canals. We have only a few little pathways, but all the rest is made of canals. And then it was logically that we must find an area where the boats can stop and can collect and exchange their goods. You have with magnetics a great variety, at least with all geophysical methods. You measure one physical parameter, and to get an anomaly, there could be several reasons to produce a magnetic anomaly. Even if you throw a piece of iron in the ground, we will have a nice anomaly. But our task is it now to discriminate different kinds of anomaly, to analyze the remanent magnetization, the direction of the magnetization, and so on, and to find out which is artificial and which is natural. And this helps a lot, but we never ever can say that definitely we found a specific piece of something. Yeah. So that's why Also, it's necessary to have an excavation. Of course, we see the layout of a house, and we can say clearly there's a wall and there are some rooms and there's fireplaces. But yeah, there are also other options. Of course, if you have this layout and the archaeologists tell me, I know this way of building houses in the Babylonian time, it's very typical, and then we are done. Yeah. But all others are with the canal. Yeah, you see the canal. It's, for sure it's a canal or the road, but many features are simply miracle, remain a miracle. And excavation, of course, is used to have a dating, because geophysics is without dating. You have just a layout and no information about the dates. Therefore, you can use other methods. You can use relative dating methods. Archaeomagnetism is a possibility to measure the ancient Earth magnetic field in a piece of pottery and to get a rough dating. But the final archaeological dating, you need the excavations. And we cannot measure the tablets and read the tablets by a magnetic method. So this is too coarse. Okay, so now just to show you, this is a little instrument to measure the magnetic susceptibility of the soil. And I can show you now when I measure here the topsoil. It's also very sensitive, that's why I need this. So for this topsoil, for example, we have 0.686 SE units for the magnetic susceptibility. If we have, for example, like this, sorry, I show you. This is a basalt rock, which they used also. And measuring this, you see the difference between the soil and the basalt. And then, for example, pottery or a pottery shirt, like we have here, it's burnt and it's also very magnetic. Look here. So this is the value of the pottery shirt, and it's at least 4 times more magnetic than the ground. With this instrument, with the magnetometer, we measure the total Earth's magnetic field, which is composed of the magnetic susceptibility of the soil and of the Earth's magnetic field and the remanent magnetization. And here we measure only the susceptibility. So so we have 2 components in one, with the total field magnetometer, which is more sensitive or like this, but at least we get an idea what is the part of the remanent magnetization of the material and what is part of the induced magnetization. And for physicists it's very important to understand. And for the interpretation of the archaeological data it's also important, because then I can discriminate if we have a kiln, a pottery kiln, fireplace, or if we have simply a pit which is full of rubbish, which is also more magnetic. So I have my reasons when I propose an interpretation, but then we have to discuss the possibilities. And it's true, sometimes I'm wrong with my interpretation, but also sometimes I must explain the archaeologists this cannot be a mud brick house when I see clearly a burnt brick. Yeah, so there is a clash of methods, and then we must leave it open, this question. But this is what science makes interesting, yeah, to discuss and to make mistakes and to find try and error. So this is normally in science. I started prospecting very early in my career. Soon after my diploma, I had the opportunity to build a device which allows us to collect magnetic data automatically. In the 1970s and 80s and 60s, it was common sense that you measure a point, magnetic point, wait a second, write down the data and continue the next point. And to do this, you are a little bit quicker than excavation, but not very much. If you want to cover a large area, you have to automate the data collection and to make it available very quickly to computers. And in the 1980s, it was the invention of the personal computers, and so this was a time where the first handheld computers for the field came up. Previously we had also a big computer in the field, but it takes a lot of batteries with us and you have to carry the batteries, and then it was connected with cables and so on, which are also magnetic. So the use of these big computers was not very time saving because you have to set up these computers for the measurement. Then some other can write it down. But I was skilled in building up electronic devices and to build up geophysical instruments, and that's why I came up with the idea to combine magnetometers with a handheld computer, with a field computer, and to collect data automatically. And therefore I designed an interface to collect data automatically. So in the way that we walk with the magnetometer, and the same time there was the invention of these cesium and rubidium magnetometers who measures 10 times a second. So the idea was that we measure continuously on a profile and we collect the data. And of course in the very beginning it was not possible to collect all the data, so we decided to collect data every 50 centimeters. So I built this instrument with a wheel device system where we had a wheel, and every half meter it gets a switch and collect one data set. And then it was the time of computer cards. We found that one profile of 20 meter and half meter spacing is just one card of data. So we made every profile one card and then transferred this card later to the big computer in the laboratory, in the computer department, which was just growing at these times at the big universities. And that was a great challenge because the archaeological department of Bavaria, they were looking for new methods in archaeology, and the Geophysics Institute was only 10 minutes far from these institutes, and then they had the idea to install a permanent position for geophysicists to do such prospecting work for Bavaria. And at that time it was, Bavaria is a separate country in Germany. They always want to be the best. Like in football, they want to be the champions, and they understand if we have the geophysics in the archaeological department, we are the champions in Germany with archaeology. And that was a great chance for us to develop and further develop this method for rescue archaeology. First of all, we did air photos and we selected archaeological sites for prospecting. And of course, we selected the most suitable sites for our prospecting. We were not taught by archaeologists to tell us, please measure here or measure there, but we go out and find a place which was suitable for us. And then we had great results and everybody was, oh, amazing what this method can do. And that was a method simply to save archaeological features beneath the ground, because we can say here, for example, is a Roman castle, and please tell the farmer not to plow too deep and maybe leave it as grassland and so on. and that was a main issue. And beside the Munich department, it was only in Paris a group, in Italy a group, and in England, of course, English Heritage. They did similar stuff like we did, and it was some kind of an institution of archaeological geophysics. And that's how it developed. It was not only a short research project for 1 or 2 years at the university, and then produce 2 or 3 doctor absolvents, and they go and finish. But we continue doing this work, and since then, since 1982, we have continuously this measurement in Bavaria, and meanwhile about 1,200 archaeological sites which are mapped very precisely, and which go into the archive, and everyone who is interested knows there is archaeological features, and they know already what is roughly in the ground, and they know what they preserve and what is not worthwhile to preserve on the other hand. Yeah. And from there we were asked from research groups, archaeological research groups, first at the Munich University, the Near Eastern department. They asked us, please, could you go also to Iraq, and we do some measurement in Ashur. That was one of our first great object. And then later from Tübingen University, somebody asked us to measure in Troja, the city, yeah, of not playground, but the scene of action of the Ilias. And there we were very successful. We discovered the lower city of Troy by this measurement. And from this moment, everybody in the world knew us. It was in the New York Times, it was in BBC and everywhere, that the lower city of Troy was discovered by means of instruments from Munich. So they didn't even mention our names, but they said with the instrument of Munich we discovered. That was funny because they at that time also many archaeologists they look at us as an engineer. They do some work and we do the interpretation, and said, no, you must leave the interpretation to us. You are not, maybe you can do some, but the very details you will need the help of geophysics. Yeah, that's how it comes into the world. And then of course we were employed for Bavaria, and they don't wanted to let us go to foreign countries. And another nice part was when somebody of the Munich University, Hermann Partzinger, came to our director and said, I will ask you if you could give us these 2 people to go to Siberia. And our director said, yes, I always want to send them to Siberia. Take them, let them go. That was funny stuff. And yeah, but that's how it develops, and now it's very common. And of course we work also closely together with international groups, with the French team, with the English Heritage, and in Austria, for example, and also in northern Germany is a group who is dealing with archaeological geophysics at the university, however.
How many kilometers you do in the day?
One square is 2 kilometers roughly, and we did yesterday for example 20 squares, so that means 40 kilometers. And at least 80 kilometers profile, because we have 2 profiles in one.
This landscape is very easy and good for your job because it's desert, or not?
No, the ground is very heavy because it's soft, and after the rain you have every step is like in the deep snow, if you step in the deep snow. So this is it takes a lot of energy in the feet.
But I think that it's better that it will be a bush.
Yeah, of course. That is the upside, that there are no bushes, no trees on it. I just remember 3 weeks ago I was in Bolivia and we measured in the rainforest, and then we had all the trees we have to go around. So this is the positive thing, and that's why we have such perfect data here, so that we can just walk along the lines without any obstacle upside. So this is really good. As I told you, I'm a geophysicist, and the aim of many geophysicists is to understand the world, and especially with magnetic. Magnetic field is not similar on every place. It's very different on each side on the world, and it's still a very interesting tool to discover magnetic field. But for me it was also interesting to visit archaeological sites, and others, tourists pay a lot of money to visit the pyramids or to visit Easter Island, and I found it very interesting that I get somehow paid to visit these places. At least I get a free flight, and I spend, of course, my working holidays to visit these places. My children are already grown up, so this is also the background. They are not anymore little, and I'm now not anymore. I'm retired, and I'm now moved to the university and continue there. So, for example, somebody asked me, do you want to measure on a place which is a basaltic island? I said, no, it's maybe difficult, we will not get results. But then he said, yes, but it's Easter Island. I said, okay, let's try to do it. And they brought me to Easter Island, and also to China or to Siberia. Or meanwhile I visited more than 60 countries worldwide, and made some measurements everywhere, and we have a large archive of magnetic measurements all around the world. And it's interesting because of the southern hemisphere, you have completely other situation with the magnetic field, and you, at least if you are geophysicist, you have to make it understandable to other groups. Meanwhile, it's easy to buy such instruments, and it's easy explanation how to use the instruments, and so many people are doing this, but it needs understanding of what they are doing. And so I feel that it's necessary to show case studies from all over the world and show what is the result in the magnetic image, and compare different places by that. So that was my challenge, and I take it. And since I'm retired, I can do some research projects, more research projects than previously, to do such work. It depends, how the features look like depends very much on the magnetic inclination of the Earth's magnetic field. And as you know, at the pole we have a rectangular 90 degrees on the magnetic pole, and then when we go through the equator we have 0, very parallel to the Earth's surface, and then on the southern hemisphere we have a negative, or the other way around, depending on how you count this. And the features, the shape of the anomaly is very much determined by this inclination. And then, of course, you have different material. If you are on basalt underground, if you have limestone rocks beneath, or if you had sediments, whatever, everything makes a difference. Yeah. So it's always a challenge if you visit a new country and to see different geological background. That plays also a great important role in the results and in the interpretation of the results. First of all, we download the data
everything here.
Here on this tough book, which is designed to collect raw data from geophysical instruments.
Specific only for this?
Yeah, no, you can use it also for other stuff but the main point is that you have all these connectors which is not available on normal computers anymore. So we have these cables which can be connected directly to the computer and so on. And this is important, not to have a interface with USB or something like this. Okay, now I have a special download program here. So I import data. Okay, now it's done. I told you this instrument was designed already 20, 30 years ago. And at that time, data storage was
Very
poor.
limited.
And they made everything to compress the data. So in total, we have probably only 1 megabyte and we can work 3 days with it. Finally, we measure total Earth magnetic field of 2 probes. We measure the time. We measure 10 times a second. So collect a lot of data. So now we have a nice layout of our grid. We have each line, it's marked how we start the line and how we go up and down. And every blue dot is 5 meter mark. And the green is going up, the red going down, and so on. So this is now our map. And in between all these blue dots, there are a lot of data, depending how quick you are and how quick you measure, how much time you need between the 5 meter line. And as you see, it's at least without any mistake. We have another one here, for example, there's a little mistake with the switch, but we can correct it. And that's what we do now, one by one. Yeah. So we calculate, first of all, a shift of the line, because our probe is 50 centimeters and we have an overlap of one probe of 25 centimeter. So we must shift the grid by 25 centimeter, 0.5. Then, for example, here I know Marco is going very quick and his view to the marker is a little bit tilted from his high. So I can map an offset between the line. I know his data already, so 0.6. And then it's at least normally corrected for him. So now you see the result from 1 square. So this is 140 meter square. That was just measured your last.
Yeah, last
file.
one, just
Yeah.
an hour ago.
Yeah. So now you see there are some minor de-staggering, but that will be corrected later. But you see very probably a nice ground map of a house. And now we have to do it with each square we measured today. And then we make a master grid and make a composite file. Put all the data together and then we have the map. In the first moment I would say we have a wall here, but we have to see more area. This is 40 by 40 meter and it can turn out that it's a wall which belongs to a huge building. So it could be one room here and fireplace and yeah. So we have to look everything together, to match everything together to make a first interpretation. You know, we have many options with magnetics. It's not very simple, that you have one signal and you say this is this is a kiln, or this is a wall. The wall can be from limestone, then it's white, and if the wall is from brick, it's black, and there are so many options. So this is not the final thing. So we can also invert the things. Maybe something will be more clear, but I'm pretty much sure that we have a nice ground map of a house with a kiln inside, and maybe a corner where they have a lot of pottery, which is a high magnetic field. But from this, it's not enough. So I of course, it's very much more than you may excavate in one campaign, 40 by 40 meter. They will work probably 3 months to excavate it. But for us, we need to understand the whole area.
Still open to the morning.
Yeah, we are all standing on the shoulders of our ancient fathers and grandfathers, and there were a lot of previous work was done by Martin Aitken in England in the 1950s. He first invented, he built a proton magnetometer, and he first did magnetic prospecting in England. And there was another person, Erwin Scholar in Bonn, Landesamt, Rheinische Landesamt in Bonn, in Germany. He was a physicist, he was archaeologist, and he was engineer at the same time. He had 3 doctor titles in this field of science. And he did a lot of research on soil magnetism and so on, and all this material was already there. I was only on the shoulder of these people. For example, at the time when I started this work, it was very common to say that this magnetic anomaly occur because somebody makes fire and produce magnetic minerals which are in the topsoil. And whenever you build something, these heavy minerals come to the ground, and then you make the measurement. So that means whenever you want to measure magnetics, there must be somebody must use fire. And my doctor thesis was, for example, we found also wooden constructions which were never burnt. They were built in clay and in the clay soil, and the wooden constructions were left in the ground, and they become magnetic. And we found pits of rubbish, of vegetable rubbish, which contain also a lot of magnetic minerals. So I came up with the idea it cannot be only the fire, it must be also some other process who produce magnetite in soil. And then I get in contact with a pope of iron oxide in soil. It was Udo Schwertmann in Munich. He was searching all his life on of iron oxide in soil, only iron oxides, because they are responsible for the color of soil. And I told him, yeah, we find magnetite in some places which must occur in this place, must be new formed in this place. And he told me, no, we never find magnetite. You need energy to produce magnetite. And then I came up with the idea, why not leave this task to animals to produce the magnetite? And then I was searching for this bacteria, and I was hunting magnetic bacteria with a simple magnet. I attract these animals, and I put it under the microscope, and I saw that they swim in the direction of the magnetic field. And that was the solution. So we found that the traces, the fossils of these bacteria, they are accumulated in organic material in the ground and makes also a magnetic anomaly. So that was one step forward in the interpretation of archaeological features. Yeah. As nearly every branch of science, we are not at the end of science. Yeah. So, very recently there were developed some new magnetometers, flux gate magnetometers, but which measures very similar the total Earth magnetic field, like the cesium magnetometers or like the proton magnetometers. And these instruments are measuring magnetic fields 200 times a second, yeah, 200 times a second, and that makes it suitable to use it on a drone. And this is now at the moment under development by my colleagues. I was also taking part of this development recently. We published a paper in Journal of Archaeological Science about this drone prospecting, and this seems to be the method of the future, to fly a drone on areas which are sometimes not accessible, and moreover you can cover large areas very quickly with it, but still there needs a lot of development because the drone itself is very magnetic due to this strong motors. So you have to deal with this disturbance of the magnetic field and the tiny little variation of the Earth's magnetic field due to the archaeology. And there's also some research going on drone prospecting with radar, but this is even a little bit more complicated. But I think this is a method which is suitable to cover large sites like this here. Of course, in Europe, where you have a solid ground, you can use also motor device systems, and you put the magnetometer far behind the car, and then you can also measure large areas very quickly. But it's always the challenge to discuss with the farmer if he let you go with your car on this field, so like everywhere. But this is a big perspective for the future. And then again, we are in the interpretation of the data. So there is a lot of things to do and a lot of research which has to be done. And also finally in the interpretation, yeah, to compare. In Bavaria we did this, for example, we measured all the Roman castles, and we can compare 20 Roman castles by their results in Bavaria. So we have a nice comparative database for our measurements, and also some other typical archaeological sites from typical archaeological periods which can be surveyed. So there's a lot of things to do. In Bavaria we have 50,000 archaeological sites, and we measured after 40 years 1,000. So there's a lot to do, and then you see all this new discovery in the New World, which people were not aware of it. So this is, and here is, of course, the problem is always to transport a drone in such a country. Yeah? This is a challenge, because you can use it also for bad issues, for militaries and so on.